Hello and welcome to lecture 56 of the course Theory of Computation. Right. In this lecture, we will see yet another NP complete problem called integer linear program. Okay. So this is a very common, well-known problem. So before seeing integer linear program, let's see what is linear program. Right. So sometimes it's called linear programming. It's a very well-known technique to solve questions and has a lot of applications, right? So linear programming is the problem. So given some constraints, you want to maximize an objective function, and you have to choose some variables x1 to xn such that subject to these constraints you want to maximize some objective function. And the thing is that all of these, the constraints and the objective function, all of them are given as linear inequalities or in the linear form. So the constraints are like a11 x1 plus a12 x2 up to a1 and x1 less than or equal to b1, a21 x1, a22 x2 less than or equal to b2, and so on up to am1 up to am1 x1, am2 x2 up so on less than or equal to bm. Sometimes it is represented as in the matrix form. So A, which is a matrix, like x, which is a vector of the variables, less than or equal to another vector b. Right. So A is an m by n matrix, x is a n by 1 vector, and b is a m by 1 vector. Right. And so these are some linear constraints, and the thing that we want to maximize is also expressed in the linear form. So it is summation of ci xi. So this also can be written as the dot product of c and x, two vectors, right? So this is a linear programming setup, right? So this is one of the standard forms. There are also a couple of other forms in which you can write it. Like for instance, you can remove this greater than or equal to 0 constraint, right? So there are a couple of other forms. The point is, this is a very given a1, a2, this matrix A, and given the values b and given the value c, given capital A, b and c, by that I mean the entire coefficient matrix A and the entire this matrix, this vector b and the entire vector c, we want to determine what are the xi's x1 to xn that maximize this sum satisfying this criteria, right? In fact, okay, satisfying this entire criteria, right? So that is a linear programming problem, and it was formalized during the Second World War, right? So in fact, I think somebody from the Russian side formalized this because see, the thing is, you have some constraints, right? So these indicate constraints, and like you want to maximize, let's say you want to maximize the benefit, right? And you have some constraints with which you have to which kind of restrict you, right? So if you think about war situations, you can imagine there will be many constraints on how you can operate, right? There will be limitation of supplies, there will be other risks being exposed to the enemies, etc. But at the same time, you want to maximize something. Maybe you're like carrying food from one place to other, and you have to carry many items of food so that it will be effective. But then you don't want to carry in such a way that you are seen by the enemy or something like that, right? So the point is, there will be many constraints, and you want to maximize some benefit. So this is kind of naturally occurring, and the linear programming setup has many applications, right? So many applications use linear programming. So one is, let's say, food. I already mentioned food in a slightly different way. So suppose you have to make a certain let's say, so one of the thing is, let's say you have let's say cat, and you want to make cat food, and you have ingredients that are available to you, right? So now the thing is that the cat food or any prescribed food, like this is supposed to be a balanced meal for the cat, right? Now I want to prepare a bag of cat food which has, so it has, let's say, each nutrient, let's say protein or carbohydrates or like some minerals, all of these has to be in certain proportion. Right? We don't want to have too much of a certain nutrient. We don't want to be deficient in some nutrient, right? So we want every nutrient to be within the permissible limit, upper limit as well as lower limit. At the same time, we have some, let's say 10 ingredients. So the first ingredient may provide some nutrients in some quantities. The second ingredient may provide some other nutrients in some other quantities, right? Third ingredient, so on. Now, how much of these ingredients should I include so that all the nutrients are there in the balanced quantity? At the same time, I want to like optimize on the cost, right? So each ingredient comes with a certain cost. So I want to pick up the ingredients in such a way that my overall cost is minimized without compromising on the limits that are imposed on me, right? So what is the best way to do that? So this is a food related question. Transportation, you are like trying to do, you have some resources, let's say you are an airline company and you want to optimize on how your fleet operates, right? So this is another, so I'm not getting into the details, but another thing is scheduling. You have some scheduling constraints, right? So any real world application where you have multiple constraints and want to meet something, usually you can write it as a linear program, right? So linear program means you have this linear constraints and linear objective function and you want to maximize or minimize. So here I have written maximize, but sometimes there are minimization versions also, right? And the linear programming setup can be solved efficiently, right? The decision version of linear programming. So here it is about maximizing something. So instead I could ask, is there some number t such that the sum of ci xi is at least t, right? So that will be a decision version of the question, right? So the decision version is in polynomial time, right? There are multiple algorithms for this. So George Danzig invented what is called the simplex algorithm, which is not a polynomial time algorithm in general, but usually it runs in polynomial time, right? So if you want to learn more about it, maybe you can refer to the simplex method. It is very practical, but it is theoretically not polynomial time. Later, I think Kachian and Narendra Karmakar, they came up with other algorithms which are in polynomial time, right? So the point is linear programming is in polynomial time. However, if we make a very small change to the setup, right, this problem becomes hard, right? So what is the change? The change is that, so here I don't have any constraint on xi except the constraint that are defined by these inequalities, right? Now in addition to these inequalities, I impose a new constraint. And the constraint is that all the xi have to be integers, right? So the same thing, but I am saying that the xi can only be integers. So this actually changes the whole thing, right? So the new constraint is that with the additional constraint that these xi's should be integers. So now, and this makes the problem hard, right? So just to give you a small flavor, the thing is that in case of a linear program, let's say some constraint is not met, then we can gradually increase x1, right, or gradually increase x2 so that the condition is met, or gradually decrease x1 or x2 so that the condition is met, right? So you can do a lot of fine tuning because there is no requirement that these xi's are integers, right? So for instance, if you slightly reduce x1 or slightly increase x2, you are not going to be changing this significantly, because if you make minor changes, you are still kind of going to be in the same ballpark, but that may increase the objective function even though by a small amount, right? So these minor things can be tried. However, if we have the restriction that these xi's are integers, we are no longer able to do these minor adjustments, because you have, like, if x1 is 3 now, if you want to try to move it, you can only move it to 4 or you come down to 2. You don't have the smooth range in which you can change the xi's, right? So that is what makes it hard, right? So one may think that restricting to integers actually reduces the search space and makes it simpler. No, it actually reduces the flexibility because it's more constraints and you don't have the smooth range where you can change the xi, right? So this additional constraint changes the whole situation, and we'll see that this additional constraint makes it NP complete, right? So NP complete means we generally believe it's not possible to solve it efficiently, whereas without the integer constraint the problem was in P, right? So in fact what we will see is a special case of integer linear program called 0-1 ILP. Okay, so in fact here what I am saying is I am not even saying that it should be integers, the xi should be integers. I am saying that the xi should be 0-1, right? Xi should be 0 or 1. So let me just state the decision version of the ILP, 0-1 integer linear program. So ILP is just short for integer linear program, right? So the decision version of the general linear programming is like instead of asking to maximize or minimize, I already said we could ask is there an xi such that the summation of ci xi greater than t, in which case it becomes yet another constraint, right? So basically you want to find some x1 x2 up to xn which meets some set of constraints. Similarly, the decision version of 0-1 integer linear program is given matrices A and B, do they exist so maybe I'll just change things slightly. Do there exist or does there exist x1 to xn such that this is true? So maybe I can just explicitly write x1 to xn in 0-1 such that these conditions are satisfied, right? So this is the 0-1 ILP, right? If instead of 0-1 if we make it integers, if the range is integers, then it becomes general ILP, right? So maybe I'll just, it doesn't look very nicely written. Okay, so this is the decision version of 0-1 ILP, and now we are going to see that this problem is NP complete. Okay, so the decision version of 0-1 ILP is NP complete. This is not that, this is also very simple to see. It is going to be in NP because you can do the same thing as before, you can guess and verify. You just guess which xis are 0, which xis are 1. So for each xi you guess 0, 1, 0, 1, 0, 1, and then you verify it, right? So this is the standard thing, you verify whether it meets the constraints, right? And to show NP hardness, we reduce subset sum to 0-1 ILP. So given a set S and a target sum T, we want to build a ILP such that the subset sum instance is a yes instance if and only if the ILP instance is a yes instance, right? So given a set S and a target sum T, we want to build a ILP such that the subset sum is a yes instance if and only if the 0-1 ILP is a yes instance. So do there exists x1 to xk such that so this is the I'm just writing down the ILP such that s1 x1 x2 x2 etc sk xk is at most t, that is 1, right? So b1 is t, and then the second inequality is the negation of this or the LHS is negated minus s1 x1 minus s2 x2 and so on until minus sk xk. So the coefficients are minus s1 minus s2 up to minus sk less than or equal to minus t. So instead of b2 it is minus t, right? And then we want all the xi to be from 0-1. And it seems very simple, right? So given the subset sum instance, we can easily write this down. So both the set elements and this target sum feature here and as well as here. This is equivalent to the subset sum instance. Why is that? Because you multiply this entire equation 2, inequality 2 by minus 1, we get this. So the LHS is s1 x1 s2 x2 dot 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 sk xk, right? Which is the same as LHS of this, and the RHS from minus t it becomes t, right? So we multiply the LHS as an RHS, but the inequality flips, right? So when you're multiplying with -1, the inequality flips to greater than or equal to. So now we have 3 which is equivalent to 2. Now we have 3 which is equivalent to 2, right? And if you combine 1 and 3, right? 1 says that s1 x1 x2 x2 plus sk xk is at most t. 3 says that it is at least t. So combining this, we get that the sum of si xi is equal to t, right? But now you have a sum equal to t. But what are xi? What are xi? Si are the numbers in the subset sum instance. Xi are 0, 1, right? So it is, let's say those I for which xi is 0 is like excluding that s. Those I for which xi is 1 is including those s, right? So basically the xi's are just picking out some of the si's, sum as in SOME, right? So if there is if we can choose xi to be 0, 1 such that this is true, then all we are doing is adding some subset of the si's, right? So this is equal to t if and only if there is some subset of capital S that sums to t, because that's what this is doing. Whichever ones are 1, we are picking out those, right? Whichever ones are 0, we are removing those. So this is actually equivalent to the subset sum problem, right? So we wrote the 0, 1 ILP instance and we said that this is equivalent to checking whether there is xi such that summation si xi is equal to t, but that happens when there is exactly when there is a subset of s which sums to t, right? So what we end up with is the subset sum problem, right? So this is equivalent to the subset sum problem. So given the subset sum problem, the writing down this instance of 0, 1 ILP was easy because it is just straight from the subset sum problem. It's almost like writing down this instance. So this is polynomial time producing the instance, and once we have the instance, the correspondence is also straightforward, right? It's clear that if this is a S instance if and only if there is a subset that sums to S, and if there is a subset that sums to S, then this is obviously a S instance. Hence the correspondence is also true, and therefore we can infer that, or we can conclude that the 0, 1 integer linear programming is a NP complete problem, right? So that's it. So we talked about linear program, which was linear constraints, linear inequalities, and subject to these linear inequalities, we want to maximize some linear objective function, and we want to pick out x's that do this, right? So given a matrix of A, vector B and vector C, we want to pick out x's that maximizes linear objective function subject to these linear constraints. And what we saw was the integer linear programming, where we have the additional restriction that the x's should be integers, and this actually makes it harder. And what we showed was that 0, 1 integer linear program, which is actually a special case of integer linear program. We don't allow any integer, but we are only specifically allowing 0 or 1. Not even like so we are only 0 or 1, right? We cannot allow anything in between. In this case is NP complete because the membership in NP is easy to see. The reduction is a reduction from subset sum, and once we have a subset sum instance, we can easily write down a 0, 1 ILP instance which is a S instance if and only if the subset sum is a S instance, and it's quite straightforward to see that this is a S instance, and that completes the proof that 0, 1 integer linear program is NP complete, right? So that completes the proof that 0, 1 integer linear program is NP complete, and this also completes the time complexity part of the course, which is chapter I think 7 in the textbook, right? This also completes week 11 of our course. So what all did we see in week 11? We just saw many NP complete problems. We saw that clique is NP complete. We saw vertex cover is NP complete. We saw Hamiltonian path is NP complete, right, which are problems based on graphs. We also mentioned a couple of other problems, but we didn't do detailed proofs of them. We left them as exercises. Then we saw subset sum is NP complete, right, which was given a set and a target sum T. Does there exist a set, subset of the set that sums to the target sum? Then we saw that knapsack problem is NP complete, and now we saw that 0-1 integer linear programming problem is NP complete, right? So, and the fascinating thing about the integer linear programming is that linear programming without the constraint that it is integers is polynomial time solvable. But when you put the condition that it is integers, the numbers are integers, then it becomes hard. It becomes NP complete, right? So that is all that we saw in week 11, and that completes the time complexities chapter. And the next week, week 12, we are going to do an overview of the space complexity aspects of the course. So just like we saw time complexity, where we are bothered about how much time we spend to solve or decide on a question. Now we will be checking in the space complexity, we will be checking how much space or how much memory we need to answer a certain computational question, right? So this is going to be the idea in space complexity. So that we will see in the next week, week 12. And that's all from me for week 11 and lecture 56. So see you next week. Thank you.